Welcome to this session of Shadow the Scientist. My name is Jamaica Marshall, and I'm pleased to serve as the coordinator for the Shadow the Scientist initiative. Shadow the Scientist is housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California at Santa Cruz. In this session, exploring the local neighborhood with the Gemini North telescope, we have the privilege of shadowing members of the Gemini North science team as they perform evening observations. The International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located on Maunakea in Hawaii and Cerro Pachon in Chile, which are two of the best observing sites on the planet. The Gemini North Telescope in Hawaii on Mauna Kea is a part of the international community of observatories built to take advantage of the superb atmospheric conditions on this long dormant volcano, which rises 4,214 meters into the dry, stable air of the Pacific. The telescope is operated remotely by the Gemini science team from the control room of the base facility in Hilo, Hawaii. Both of the Gemini telescopes have been designed to excel in a wide variety of optical and infrared capabilities. By incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers and the Gemini partnership explore the universe in unprecedented depth and details. With locations in both hemispheres, the International Gemini Observatory can collectively access the entire sky. Now you're in for a special treat. As you can see, observations are already underway. We have a full control room for this session. So not only are we joined by several members of the Gemini science team, but we have special guests in the control room as well as joining us in the Zoom room here. So how about we start with our special guest online, and this is Ekta Shah, who has joined us for many Shadow the Scientist sessions as a science host, as well as a member of one of the research teams that have used Gemini North Telescope. Welcome, Ekta Shah.
Thank you, Jamaica, and thank you everybody for having me. It's a pleasure to be here all the time. And so I just completed my postdoc at the University of California in Davis, and my research basically focused on discovering massive protostructures, massive structures of galaxies in the early universe and studying their impact on galaxy properties such as their black hole activity and star formation rate. And I'll be happy to describe more about that later on in the session. And yeah, as you mentioned, we have used not just Gemini telescopes, and we plan to use Gemini telescope for some of these structures in the future as well. But we have also used Keck telescopes and Subaru telescopes, and we have done a lot of shadow sessions there as well. So those of the participants who have been here before, you might have heard about from our team, and in the future also, I'm sure we will have sessions using more facilities as well. So thank you for organizing this, and I look forward to answering your questions and participating in this as well.
Excellent. Thank you so much, Ekta. And also with us in the control room is our normal cosmic guide on this stellar journey, Brian Lemo, with a lot of amazing guests. Brian, do you have a second to say hello?
Yeah, I do. Hi. Hi, everybody. I'm Brian Lemo. I'm a staff scientist here at Gemini North. I am observing tonight with Eunchong Kim, who is a new science fellow here, who just moved to the islands from Korea. It was, what, a month and a half ago, 2 months ago?
Yes, 2 months ago.
Yeah, okay. So Eunchong is in the observer's chair tonight. I am helping with that part of the observations. And then we have Mateus Rodriguez back here in the operator's chair. And we can talk about what those chairs mean in a second. We have an incredible night on Maunakea. We have absolutely gorgeous skies. There's not a single cloud in the sky that I see. And we have an incredibly stable and non-turbulent atmosphere, which is really, really great for our observations. So for those of you who know what seeing is, we were getting about 0.3 arc-second seeing earlier tonight. And that's actually, we're still getting 0.3 arc-second seeing. So that's absolutely incredible. That's like 99 percentile best on Maunakea. So we're very happy. Right now, we're taking calibration observations to calibrate one of our instruments. We are just about to move to another instrument. So we're just kind of getting ready to make sure that we understand the properties of our instruments before we start really delving into science tonight. And so that's the plan. So I'm going to kind of be bouncing in and out to help with the observing, but I'm very happy to answer questions, and then we can take time when things are a little bit less frenetic. We could take some time to talk about some of the observations that we're doing today. And so we're also joined in here with the Hilo professor and several students from Hilo. We're actually on the Hilo campus here. And so they're our neighbors. We're not on top of Maunakea. We're at 300 feet above sea level rather than 14,000 feet. So much more comfortable down here. So Mariana, would you like to introduce us?
Thank you, everybody, for having us here. Thank you, Jamaica, for making this happen, and Brian. And didn't know I would meet another Chilean person here. I'm also from Chile. And so I am actually teaching stellar astrophysics lab. And so these are half of my students. The other ones couldn't come, short notice. Sorry, guys. So we've been looking at data from GMOS, data actually from the archive as well, and looking at the stars that you guys are getting. I was going to ask my students to also look at that. We're pretty stoked to be here. Even though we are next to Maunakea, we don't really have a lot of opportunities to go there. So this is superb. We observed with a 2.2. Some of you observed with a 2.2. I think you observed with other things. But, you know, sometimes we don't take advantage of this. So thanks for this opportunity. I used to be a science fellow a long time ago, 20 years ago. So this is like coming back home, but it's a bigger home now because you guys make a huge extension out there. So yeah, we'll talk more, but if you guys have any questions. Oh, there's people from Chile as well. Aloha.
Welcome. Yes.
All right. Maybe Spanish. Right, Matthias? Martin?
Yeah.
Chile and Spanish is different.
Another language.
We are so thrilled to have you all with us for this session, and certainly look forward to any questions you might have. Feel free to ask those anytime, as well as those of you joining us virtually. We welcome your questions and comments at any time in the chat, and we'll certainly get to them as the time allows. So maybe we can go over to Matthias. Can you get us started with what's going on tonight? We have amazingly clear skies. The seeing is stellar. Talk to us about why that's important as you're getting started for observations.
Yeah. So we have spectacular conditions about Maunakea. Right now, we are taking calibrations, but we are using mostly 3 instruments right now. 2 of them are main instruments. One is GMOS, and the other one it's GNIRS, which observes in the near infrared part of the spectrum. So, and also we are observing with MAROON-X, which is a visitor instrument that it's usually used to observe radial velocities at high resolution in other stars and also other planets. So we need we are here in Big Island because we have usually we have these really good conditions, weather conditions. So because of we are at the middle of the Pacific, we receive all these layers of dry air from the Pacific, which makes the atmosphere pretty stable for this kind of observation. So the atmospheres, which is made of a bunch of gases, sometimes when it's turbulent makes us more difficult the task to observe with a better view of the cosmos. So you can imagine this, which we call seeing, as being under the water on a pool and looking to the surface of the water like the sun. Under the surface of the water, you will see the sun pretty distorted, a lot of waves. So we see the same things when we check to the sky and we are here on the surface of the planet. So all the atmosphere perturbs the wavefronts, the light coming from the stars, from the galaxies, from all the cosmos. So here it's pretty stable. We are pretty lucky. So that makes us easier to investigate and do research, take good data. And tonight it's a clear example of that. The thing is pretty stable, stars look sharp. And also another thing to take into the game are the cloud coverage. Maunakea, it's pretty high. It's like 13,000 feet high. So usually because of the same layer of stable air, it puts the moist air close to the ground, and the sky is pretty clear usually. And right now it is like that, perfect conditions. So we have different grades for the image quality, which is the seeing, the image quality. We divide in percentiles, and right now we are on the best of the best conditions. That will be like IQ 20, what we call. It feels pretty great. And same thing with the cloud coverage. We have different percentiles. And right now we are in CC50, which is most of the 50% of the time we got these conditions. And regarding image quality, only 20% of the time it's like this. Good.
Let's go back.
So we're pretty stoked. It's pretty beautiful, and also
No. Like, so let's set up.
we have company. So yeah, pretty much that's what's happening. I don't know if Brian is sharing the screen, right? Is that what you're seeing right now?
Yes. So I think we're seeing the weather right now, Mateus.
1 second.
Awesome. So you can see the cameras. Those are the cameras from the Keck Observatory, and you can see that it's pretty clear. We have
300 seconds.
big moon, shiny moon, that it's making the skies to glow, but otherwise it's pretty beautiful out there. And before after sunset, we got a nice comet that was shining. It's an incredible spectacle out there. So if you have the opportunity during these days to go to some place that you can see the horizon on the west, please go and enjoy. It's pretty visible naked eye.
Yeah, we can.
And I think we have a privileged place here in Big Island to take a look on that shiny comet. Wonderful.
And so
Yes, this is the Comet Atlas A3, right?
Exactly.
I've been trying to catch a glimpse of it myself, and since I've been not feeling so great, I haven't been out, but a friend of mine caught a great view from on the Kona side yesterday, and I've seen many amazing images already from it. So I'm going to try to catch it myself.
Good luck. I have no doubt that you will.
I hope so. So you are you're a science operations specialist is one of the roles that you're in. And so in that role, you are in charge of the telescope, its safety, and making sure everything is running smoothly. Can you tell us a little bit more about your role?
Sure thing. So I work as a science operations specialist here at Gemini North. I like this position a lot. It's pretty dynamic. We have multiple duties, four main duties. We run telescope operation mostly. That means that we move the telescope where we need to. Gemini Observatory is a Q observatory. We work observing multiple proposals that the scientific community make through the semester. So they make a bunch of proposals, all the scientific community. We pick up the best ones and we organize them to be observed during the semester, right? So each proposal, each observation has their own weather constraints, as we were talking about the image quality, the cloud coverage, and all that. So regarding the current weather conditions, we are choosing which observations to make. So as an operator, which is what I'm doing right now, we run the telescope operations in the sense that we move the telescope to different points on the sky regarding the proposals, the observations. So in that sense, we are in charge of the safety of the whole instruments, the telescope indeed, and the observatory, of course. Right now it's pretty smooth. So if the observer, which is in the other chair where Brian and Hong Chong is, they tell me where to go and I move the telescope to that place. They ask me pretty nicely and I can go, otherwise I might not. So that's one of my duties. Also, I can be the observer, which is what Brian is doing right now with Hong Chong. And they can explain a little bit more what is that about. And also as the science operations specialist, we run telescope operations during the day. During the day, we also move the telescope a lot sometimes because we need to test a bunch of stuff regarding the instrumentation. So we have engineering tasks and we need to be here in the control room during the day. So if somebody wants to do something with the telescope, we allow them to do it and we make sure that everything is safe to do it. So during the day, we have a day crew that goes up to Maunakea and they make sure that everything's working. I just press buttons here, but they are the ones that make this thing to work. I mean, we all make this thing to work, but they go up during the day, and as a day SOS, we are here coordinating everything that must be done during the day. So everything is prepared for the night. And also, we do projects as a science operations specialist. If we are not moving the telescope or picking up observations, we are doing project time. And that can be anything that improves telescope operations or also that improves relationships in Nova Lab inside Gemini and everything that can improve ourselves. So in my case, my main project is to do some outreach images. So if you see beautiful images around there, I might be involved in that. I love it. I started as an astrophotographer and then I studied astronomy. Also, I did my research and it's a passion that I have, and it works pretty nice here because I can pick up the beautiful data of Gemini Observatory and make some images so people get interested in astronomy as I did. So it's a pleasure for me to do this, and I'm glad I have the time to do it as my work, because for me it was a hobby and right now I can do it also on my job. So that's pretty much what is an SOS. We're ready to zoom? Yep. All right, I need to move the telescope. So give me a sec.
You're all set up to go.
Save and erase it.
We can take care of the bookkeeping afterwards.
Could you do one?
Do one?
Yes, the calibration.
Oh, the 16.
Yes, right.
Perfect. Thank you. Thank you, guys.
Yeah, so I'll step in here for a second. Yeah, as Meti said, so he's basically the driver tonight. myself and Chong are the ones with the map. We're the annoying ones in the passenger seat with the map.
The current weather.
And so
So they told me that
kind of know where to go.
these observations, there are a bunch of calibrations. So here's here, import this, and just by pressing this button,
and we have the ability to kind of zoom in and see the fine details of where we're.
a diagram.
So we're the people that are kind of giving advice to Matthew, saying, no, go there, go there, go there, go there. No, stop. Oh my gosh. And Matthew, as he said, is driving. He's making sure that all the things associated with the car are working well. And he's, driving. You're the one.
I think so.
Of the safety of everybody, right? So
Be sure that the guiding
and the most important thing is that you keep your eyes on the road, that you're
taking the data,
moving
sure that the telescope is.
and we don't, a normal car may cost $10,000, $20,000, $30,000. We have
I can see it has
tens of $million telescope.
different sensor, not the one I'm using.
And so this is a very, very expensive car that we have. And
You can see here on the TSD telescope status display. They can hear me. But it appears where I'm going now, and the telescope it's moving.
If you work hard,
But you cannot see from the cameras, but
there's only one. Well, there's only two.
see the telescope actually.
Wait, Brian.
Oh,
Here we go.
you did. Did you guys?
I think I accidentally.
No, I was hearing you all the way up until like 2 seconds ago.
Oh, okay. Oh,
I think I accidentally mute us.
oh, okay.
Sorry.
Okay. No problem. So all good. If you were to like crash your car, that would be a very bad thing. But there's a lot of cars on the planet, and it may be that it may be painful and it may be financially difficult, but eventually you might be able to buy
We
another.
are taking high resolution spectra.
But there's only 2 Gemini telescopes,
Just moved, and I'm gonna
right?
an
And
image
all
of the
the
field.
specialized equipment that we
I put everything on center.
the stuff that we
I
have,
will center the field, and it's pretty
electronics
close.
doesn't even exist.
We
Or there's
didn't slew so far, so
in it, and so
fine.
it's very
I play some offsets.
non-reproducible equipment.
I'm gonna stop reading out. And now I will send the
Acted-
to the wavefront sensor.
Yeah, sorry, my hand's up. Just to
Oh, sorry.
quickly, we're hearing you and Mateus, and I want to hear one of you very well. It's kind of crossing over. I'm not sure how we can fix that. Oh, was that what were going to say also, Ekta?
I don't know what.
Yep.
Oh, thank you so much.
Oh, you guys are good. Okay, can you hear us okay now? And then we move the microphone, so hopefully you can hear me when you want to hear me, and then we can hear Matty when we hear Matty. So can you hear me okay, and Matty a little bit less now?
That's right. Perfect.
Okay,
Thank you.
perfect. Yeah. So again, so Matty's in charge of the safety of the telescope and all the instruments because it's very hard to. We only have a couple of those, subcomponents for different electronics. I mean, first of all, it's very expensive, but even to replace any of this stuff, if it's even possible, we have to locate the 1 or 2 that exist on the entire planet. So it's not equipment that we can easily reproduce. So Matty was slewing to our location. I'm going to bring this up. So this is our telescope status display. This is giving us a bunch of information because, of course, we're not on the summit of Mauna Kea. We're down here in Hilo, and so we need tons of sensors. Otherwise, we're operating not next to the telescope. We need to make sure that the telescope is working, that it's pointing where we want it to be pointing, that there's no undue stress on different parts of the instrument or instruments or telescope structure. We need to know the weather. We need to know the humidity. We need to know the amount of wind that's coming in. We need to know that all of our subcomponents, so our mirrors and our wavefront sensors and all these things are operating correctly. This is a broad view of all of that. And there's a ton of numbers on here. That's not, we don't necessarily need all of this at any given time, but at some point, each one of these numbers here may become useful. And so it's important to have them on there in case we need to refer to them. And so, Chong, I think we're in location. We're guiding. Double check. Yeah, we just started guiding. Matty, we're guiding yet?
We are about to start guiding.
Okay. So you can take your first, yeah, there you go.
I'm closing the loops. Loops are closed. We are guiding.
Okay, thank you.
That means that.
So
I just.
yeah, 35. So I would drop that to 0.5 second exposure. Okay, so we're using this MAROON-X instrument. I'm gonna switch screens here. I'm actually gonna watch Nchong do this. So I'm just assisting. I'm the back seat driver right now. I'm the really annoying person in the back that's saying, no, you shouldn't do that. You shouldn't go that way. So Nchong is in charge of, she's in the passenger seat. And so she's acquiring our star. So our target is actually this thing that's highlighted in the green, and that's good that it's green. And so you can click the start guiding. And so we need to guide the telescope. So meaning we have a telescope that tracks as the sky moves, but we need precision that's 1/36,000th of a fingernail held at arm's length. So if you hold your arm out, you close one eye, you have a fingernail on the sky. So 1/3600th of that is an arc second, what we call an arc second. We need precision in our movement of 1/10 of an arc second. So that's 1/36,000th of a fingernail. So it's ridiculously precise. So this is important. We want to get all the photons, everything that we can get from this astronomical source. We want to get into our telescope and into our instruments. And so what you see here, you can take the image. Yeah. Maybe stop it for a sec, and then let's go 0.2. Is it no problem? Yeah.
So I know I.
0.2. Yep. And then start guiding. And then as soon as you see it guide for a second, just take the frame. Yep, it's guiding. Yep, take the frame. Yep, you're good. Yay! Starting 5-minute science.
Woohoo!
Okay, so that was a successful sequence. And so we have this guiding that Matty just alluded to maybe 2 minutes ago, where he said we're now guiding, and that's good. And so that means the telescope is guiding. We are additionally with MAROON-X. This is not every instrument has this, but MAROON-X has its own internal guider as well. So it has a little what we call like fold mirror or tip tilt mirror that's on the inside of MAROON-X, and it has a dichroic, so that splits the light. And so we throw most of the light to the instrument itself, but we have a little bit of light that goes to our guider. That's this thing here, and it keeps the star centered to 1/360,000th of a fingernail. So even 10 times better than our telescope does. The size of this fiber here, this is our science fiber. So this is what's collecting the light from MAROON-X, is 1 arc second. So that's 1/3600th of a fingernail held at arm's length. And so it's measuring every, so at 5 hertz. So 5 times every second, it's measuring the location of this star, and it's trying to use this little mirror on the inside of MAROON-X to keep that star in the same place, because the atmosphere, just like Matty's analogy there, when you're looking at the sun underwater, you see the ripples, right? And there can be more or less ripples depending on whether you're running out of oxygen and going like this. And so right now there's not a whole lot of ripples in the water or the fluid that's the air in the atmosphere. And so there's just a little tiny movement that's happening because of these ripples. And so the internal guider of MAROON-X is compensating for that. And so all of this, again, is to, we spend so much time making sure, well, first of all, a lot of money and effort to make really big mirrors on telescopes and, you know, have a structure that supports them. But making sure that the instruments are as sensitive as possible, that we, you know, when we have the incredible day crew and the SOSs that get everything ready for the nighttime, so that we're making sure that things are ready to go. That we have everything in an optimized way. All of our engineering is in an optimized way to be ready to collect observations. Myself and Chong, actually, Chong was in the National Gemini office in South Korea, and we prepare during the day observations from scientists all over the world. They ask us, so they apply for time on the telescope. They are awarded based on scientific merit time on the telescope. And roughly 1 out of every 5 people that ask for time on the telescope, they get it. So you have to have a pretty good idea to get time on the telescope. And once they get that possibility of time on the telescope, myself and Chong and other scientists here, we prepared the observations. So Mariana, probably you did this as well. So this is the phase 2 process, right? And so this can take a long time. And it depends on, you know, you could be working with a student that's never observed before, or you could be working with a world-class scientist who thinks they know how to observe, but maybe doesn't, or you could be working with somebody that really knows, you know, what they're doing. And, or, you know, but we have new instruments all the time, new modes all the time. And so, you know, it's even confusing for us. And so we spend a lot of time trying to get everything ready and optimized. Okay, so the day crew go up to 14,000 feet, they optimize everything. The SOS does all these careful checks, they optimize everything. We optimize things from the scientific side. Well, we want to get all of that light in that instrument, make sure that all that effort is not for nothing. And so that's what this is. And so right now we're getting all the possible light that we can get in MAROON-X. And this is all for a calibration observation. So this is basically to get an absolute velocity calibration, because the precision of this instrument is 1 meter per second. So it's like one of the best instruments on the planet for this type of science. It's just measuring wobbles in stars of literally 1 meter. That's like walking, like 1 meter per second at tens, 20, 30, 40, 50 light years away. Even more, actually, probably a couple hundred light years away. So it's local neighborhood stuff, but it's you know, I mean, that movement is very small compared to the distances that you're measuring. So we're just reading out now, so we are ready to move on to the next observation. So our next observation is going to be another MAROON-X observation. So we've calibrated the instrument. Oh, it's the last one of this subject. Yeah, nice. Okay. No, it's all good. You can cue it. Yeah, so that's just a phase 1 dispatch. Yeah, that's totally fine. But good that you read that. That's important. So ready to move.
Get up to 124.
So we got the data that we wanted. Thanks. Go so cd dot and go to 13. And then yeah, get remember the Yeah. Oh, sorry, that was the wrong one. So click. So you just have to click. So cancel. Yeah, and then open. And then save. Red one there. Yeah. I'll actually reload this interactively if you don't mind. And then I'll stop doing interactive right when you're ready to observe. Okay, so these are the data that we got out from MAROON-X. So this is what's called a spectrograph. It's a fancy spectrograph. It's a high precision radial velocity spectrograph. And that's just a fancy word for saying that it's really, really precise and it gets meter per second resolution. So it's a planet finding machine. It's looking for extrasolar planets, and this is from the wobble of the host star by the gravitational pull of planets around those stars. And those planets don't have to be very big for a meter per second pull. So we could actually detect Earth-like planets-ish with this instrument. So that's very, very exciting. And in fact, there's programs that are led by the teams that help build this instrument, looking for habitable worlds in the local solar neighborhood. So within 100 light years or so. So it's basically a census of all stars in the local neighborhood, and just trying to measure any chance that we see planets that are so lower mass planets that are in what's called the circumstellar habitable zone, which is basically defined as the region where liquid water can exist. So, I mean, if you're not excited by that, then I don't have anything. I mean, you might as well sign off now.
No, we're excited. We're excited for sure.
Not what I personally study, but I'm all for it. I'm like, I mean, like, why not? So yeah, yeah. Please grab the control from me at any time. And so we're gonna get ready for this observation, then I can come back to this.
Okay, sounds good. We have a question about adaptive optics when you are able to return.
Yeah, 3 seconds. You can take it. Oh, sorry. Home link and reset the plot. Yeah, good. Okay, so take a frame. Okay, let's concentrate on this one first. So let's do the P movement of +1. So ask Mati for. What we're seeing right now is we're trying to get the star, which is just at the top part of the circle. We're trying to get it centered into the science fiber. And Unchang just asked Mati to just nudge the telescope a little tiny bit. And then you can take another frame. Yeah, you can take another frame. And so Mati did that. And if we did a good job, then yes, perfect. So we're there. And so now we can start guiding. And so we're activating the tip tilt mirror in the MAROON-X instrument, and it's going to do some work to every 3 seconds now, because the star's a little bit fainter than the previous one. It's going to pull the star. Well, no, it's going to move the light path so that the star appears in the. We're not moving any stars tonight, unfortunately. So that the light goes directly into the science fiber. And so there it is. It looks nice and centered. I see like 15,000 counts. That's totally fine. It's 30 minutes. Okay. Okay, starting 30 minutes science. Yay. Okay. So now we have some time to talk. Yeah.
I have a question.
Yeah.
So these elongated dots on top of the spectrograph. So what is that? What does that represent?
Yeah, so that's our what's called a laser frequency cone. And it's an internal calibrator in MAROON-X that allows for precise knowledge of the wavelengths of each of the locations on the detector. So it's basically a way, I mean, you don't, so I'll go back here. Then we can get the adaptive optics question. Okay. Right, so this is the data that come out. It's gonna be a little bit laggy because I'm BNC. Okay.
Different channels.
Two different channels, exactly. Yeah. So this is it's a dichroic splitter. This is the blue channel, and I think it goes from like 4,000 angstroms to 6,500 or something like that. And then so basically purple as we see it to red actually. Yeah. So this blue channel is like purple. It's basically the entire range of human seeing what we see optically. And then the red is a little bit, it's our very, very red, and then starting to what human eyes would call the near infrared, so just close to infrared, but it's actually not what we call near infrared in astronomy. So past 1 micron or 10,000 angstroms or 1,000 nanometers is typically what we call the infrared. Right, so you have these two detectors, you have all these orders. So basically there's optical elements in here which disperse the light both in the X dimension and in the Y dimension. So it's kind of a cross dispersed observation. But there's no wavelength information on here, right? So like normally with a typical optical spectrograph, you might take a arc lamp exposure. Probably you've done that before. Well, that's not precise enough for MAROON-X. So basically you have to have at the same time, because you're going to take the arc afterwards, right? Generally. Well, in optical spectroscopy, you have like skylines, right? So that gives you a more precise wavelength solution than taking an arc afterwards, right? Because telescope can move, the flexure, all this kind of stuff. But we need like at every single location a skyline basically, and that's what this does. But it's internal to the instrument. That makes sense? Yeah. So we have two calibrators in here, one called the laser frequency cone, the other one called Etalon. One gives us precision, one gives us accuracy. And those are two different things. And so we want to get the 0 point right, meaning we want to get the start and end point of the wavelength solution correct, but we also want to get precision, meaning at every single location, we want to know, is there a little tiny shift in the wavelength solution? So yeah, it's crazy. I mean, it's precision that I would never care about for my observations, because I'm not trying to measure exoplanets. I'm trying to measure distant galaxies. So whether they're a little tiny bit closer or a little bit further away, not really that big of a deal for me. What was the question, Jamika?
So we had a couple of questions. First, let me go to the most recent question about aggressiveness. Back on the previous screen at the top.
Oh, yeah. Yeah.
Yeah, so right there, just above the image in the middle, aggressiveness. So the question is, what does aggressiveness mean here?
Okay, yeah, so you can change how big the movements are based on the measurement of the compensation movements of the tip tilt. So this is what this thing is up here. So you see T/T, axis 1, axis 2. It's a mirror that can move this way and move this way. And so when we see the star apparently move a little bit, there's a compensation in the tip tilt, and that compensation can be like pretty aggressive. Like it's like, oh, it's moving like, way over there, so I need to move here. Or it can understand that it's, let's average it. Let's not be too crazy. Let's not jerk the wheel too fast. So let's go nice and slow in our movements, and hopefully it'll kind of average out. It'll move back. So both of them are reasonable under different circumstances. If you really need to move fast with the wheel, okay, you need to move fast. But a lot of times you don't need to do that. You can just kind of do nice slow driving. And so we put the aggressiveness, it goes 0 to 1, where 1 is the most aggressive. We normally put it at about 30%. So it means, yeah, pretty slow movements. We're not expecting the star to move around a bunch. If we had like a really turbulent atmosphere, or maybe the telescope wasn't working in a way that we were expecting, and so that the instrument needed to do a little bit more effort to keep the star there, we might put the aggressiveness up a little bit higher. But right now, everything's working perfectly. And so we can not ask MAROON-X to do too much, because actually this tip tilt mirror, it has a limit. So, it can only tilt so much. And so if we hit that limit, we have to kind of reset things, and it's not a fun process. So that recovery time basically is like a minute, and we have to reacquire, and we can't stop MAROON-X observations. It's some subtlety of how the instrument works. So we're basically just integrating the whole time, no matter what. And so if we lose the star for a minute, in this case, it's a 30-minute exposure. We actually lost the star, for a couple minutes last night, Sean? We lost the star last night for, like 2 minutes. And that was actually because we had the aggressiveness too high. It was overcompensating, and it was a very faint source. And so it was thinking that it had moved, but it was just actually what we call shot noise. It was just noise that was kind of moving the star around. And so it thought that it was moving it somewhere else. And so it moved the mirror, and then we lost the star, and we didn't recognize that until about a minute in. And so then we had to stop the guiding, reacquire. But the data were fine because it was a 30-minute observation. So it's only, 1/15 of the observation was integrating on nothing. And so they still get a lot of signal for that. But yeah, great question. Each one of these numbers on here, I mean, you can just see like the sheer number of numbers that we have for everything. They do mean something. So it's important. Like we always, especially at 4 a.m, it's very easy to mess up, like putting in a number in the right way. So we have these like guides that we sit with, and then at 4 a.m, when we're basically drooling on ourselves, we're ready to go to bed, we look through here like, okay, set aggressiveness to 0.3. Okay, it's 0.3, got it. Okay, set guide interval to 2 seconds. Okay, got it. So it is important, and especially like if we were on Maunakea, I've observed from Maunakea many times, probably you have as well.
Without a telescope. There was no primary mirror.
Okay.
There was a structure.
Okay.
Up on the platform as well.
Oh, really?
Using our oculus.
Okay. Yeah. It's not.
But no, it was fun.
Yeah, you have to be prepared for that.
That's
kind of fun. Yeah.
There was a hole of the primary mirror going down. It was open.
Really?
And I think a cable got wrapped somewhere, and the whole table started to go into the hole, and it stopped because there was, I think, a computer that was linked to something else, and that's why everything didn't just fall down. But we were just right next to it, so you had to think very carefully. We were cold.
Yeah.
We were in, we're 4,000 meters. You have to have all those reminders.
Yeah.
Sticky notes everywhere
Yeah.
back then.
Yeah, because my brain personally doesn't work like super awesome up there.
And we would go take turns, and then another would come up.
Yeah.
Yeah.
Yeah, so it's an adventure always up there.
That's great.
Yeah, it's awesome. I was up at the Canada France Hawaii telescope, which is right next door to Gemini. And they, in their dome, they still have their prime focus cage.
Yeah.
And prime focus cage is, I'm not old enough to have ever done this, but this is what astronomers used to do. And I've been at many telescopes, including the Lick Observatory in Mount Hamilton in California, and then the Palomar Hale 5-meter telescope in the Grover Cleveland National Forest in Southern California, where they still have the prime focus cage actually, and you can climb in it if you want to. And it's sitting at the top. So prime focus is the top of the telescope. And so there's basically no secondary. You take off the secondary and you have your cage up there. And astronomers used to sit in there all night. And you had your photographic plates, and you had like not a sandwich because it would like, you'd have crumbs and it would fall, and that would be bad. So I don't know.
How do they go to the bath? That's what I don't.
They give you two thermoses, one that's full of soup and the other one that's empty.
Oh, no.
Sorry, this is a family show. Sorry.
Um, you know,
I think so. Yeah. Keep track of things. It's important in astronomy to keep track of things.
I saw as you were talking about the importance of having those guides around, especially as it gets late in the night or early in the morning. Ekta was nodding. Ekta, would you like to comment there as an observer and former student? How important was it to have those guys there as you were learning the ropes?
Yeah, I mean, my first experience of observing in Hawaii was using Keck telescope, and I was a little PhD student, I think in my first year. And it was kind of very overwhelming to sit on the observer desk and be like, I am actually managing the instruments and all, but I was very happy to be supported by, the team, like the team that we see right now. And the member over there, he was like, if you break anything, it's on me. Like, I will probably properly guide you, So that was very helpful. And apart from that, I would also say that, apart from these guides, it's also very, very helpful that, anytime you make some move or something that can potentially result in some issues, you will also get messages, like, are you sure you want to do it? And then if you are a new person, like how I was at the time, you can kind of ask somebody, like, it's giving me this message, what could go wrong, or should I do this or not? So that's very helpful. And apart from that, there's also one more thing that I found very helpful, which was you can also set up, like, every time, for example, when you make repeated observations of the same object, and so after each observation, it can also make some sound, so in our case at Keck, the sound was of like train engine, and that kind of helps you to stay awake, and for you to be like, okay, it's getting done, and I can now change information if I want to or something. Because if you put observations for like 15 minutes or something, or even 30 minutes sometimes, and if you kind of fall asleep or something, you don't want the rest of the night to go to waste. So it helps you to kind of stay alert and make sure you are using the instruments properly and stuff. So yeah, lot of guardrails and lot of technical support from the teams that we see here that enables you to function properly during these hours.
Absolutely.
Yeah, it's a good point. Actually, MAROON-X is, since it's a visitor instrument, it doesn't interface with our normal keep awake systems. So it actually doesn't have any sounds or anything like that. And so we don't know, like, when the exposure is complete. We have to keep an eye on it. And so it's on us to keep the timing and everything. And actually, MAROON-X is one of the only instrument, I think it's, okay, we could do this with GMOS potentially, but it's the only instrument that I've used where we take 4 to 5 hour observations without actually doing anything else, if everything goes well, because of this awesome guider inside of MAROON-X. It deals with what we call differential atmospheric refraction and any flexure. So these are things that cause optical distortions, basically, or the atmosphere causes light to be bent. The active optics in MAROON-X actually takes care of all of that. So if we take a really long observation, we don't need to actively do anything. And so it can, so when we do a transit observation, this happens actually very often. It's happened recently with MAROON-X. I think we took one a couple of weeks ago. And the idea is that you have a host star and you have a planet that's going around it that you know kind of fairly precisely what the orbit is, and the time when, so if the observer on Earth, it's over here, where there's going to be ingress. So basically you start to see the planet occult the star, you start to see the chemical signatures of the atmosphere, and then you see the planet go in front of the star, and then it exits the star. So those transit observations usually take 3 to 5 hours, and we'll just sit, if everything goes well, we'll just sit there integrating over and over and over again, taking new observations, looking for signs of those chemical signatures to get planetary atmospheres, which is freaking awesome. And so, it's 4 to 5 hours and we have no cue that things are actually working. So it's one of those situations where like you want to just sit there and, I don't know, read a book or, just be happy that everything is going fine, but we have no sounds, so we don't know. And so we have to keep checking and making sure everything is okay for that 4 or 5 hours. And that's just looking at the screen, making sure things are still guiding correctly and everything.
Okay, so it doesn't actually make sound even when it's losing guiding or something. You just have no sound from it. Okay.
So, we're working on that because it's you want it, as you say, you want some sort of cue that things are going wrong. Yeah, and that was part of the reason we didn't notice last night that we were losing guiding, right?
That's
Like because it was just kind of drifting and we were taking care of something else. We came back to the screen and we were like, oh, whoops, something's happening.
That's right.
We have this graph over here, which is this photon counter. That's our only kind of, it's an easy way to tell that we're losing count. So we're nice and constant in terms of the number of photons that we're measuring. And if for some reason the screen wasn't up or it was stretched in such a way that we weren't able to see things, this would tell us immediately that we're losing counts. So there was a question about adaptive optics in the chat.
That's right. Is adaptive optics, is that being used right now?
So as I mentioned earlier, we're using active optics. There's a differentiation, and I'm not totally sure about the differentiation, like where the exact point is between the two. But we're just using tip tilt inside of the instrument. And so that is actively correcting for the atmosphere, the bulk movement of the atmosphere. But we're not using adaptive optics in the sense that we're trying to change the wavefront of the light that's coming in. So the atmosphere distorts light, the wavefront of the light, so it causes these ripples. Adaptive optics is a technique that's used to try to correct for that deformation and to take the atmosphere almost entirely out of the equation, except for the attenuation of light. And so, Jamika, is that you annotating?
Is that me and annotating? No.
Okay, so somebody's annotating. Anyways, so we do have an adaptive optics system here. For that system, we pipe light into an AO instrument that has a deformable mirror. So this instrument is called ALTAIR on Gemini, and it has a deformable mirror, and that mirror is changed with actuators, like little pistons in the back, to exactly correct the distortions that are measured from light that's coming in. And so we take a kind of blurry image and we make it very, very sharp. And so the typical correction for adaptive optics is if we're getting like, let's say, 0.8 arc second seeing, which is where we can start to kind of use adaptive optics. So this is, again, roughly 1/3600th of a fingernail held at arm's length. We can increase the sharpness of that image by about a factor of 6 to 8. So it'll be 6 to 8 times sharper, the image that we're looking at. So if you're looking at a galaxy, you could look at regions that were 6 to 8 times smaller with adaptive optics than you would be able to see if you were just doing what's called natural seeing, so no adaptive optics. Adaptive optics for all telescopes in the world is only possible in the infrared because, again, you have this dichroic. So light is piped, optical light is piped into the adaptive optics instrument, and then the near infrared light is piped to your instrument. And so the adaptive optics instrument changes the wavefront, and then that near infrared light is sent to the science instrument. I I have heard rumors that in the next 3 or 4 years that perhaps there will be IR sensitive adaptive optics instruments. So that means you could do adaptive optics in the optical, which would be amazing. But that's not a capability that anybody has yet. But so we can do better, for example, than the James Webb Space Telescope or the Hubble Space Telescope, because we have a bigger mirror than both, with adaptive optics. So we can get a sharper image than either one if the conditions are right and our adaptive optics is working well. So if anybody ever says that, you know, space-based telescopes are always the way to go, that's not necessarily true, because we can have very big telescopes on the ground that are cost a lot less money. I think we could have built 100 Geminis for the same money that was spent on James Webb. And James Webb is absolutely awesome, and it does things that we could never do. But it depends on what exactly you want. And so the big telescope, the really big telescopes that are coming up, so the extremely large telescope in Chile, and then 2 concepts that are being led by the US, which is the Giant Magellan Telescope and the 30-meter telescope that may or may not be built. These telescopes can get insanely high resolution that, you know, James Webb or Hubble couldn't even come close to.
So
Yeah. So everybody has their own phase space to work in, and you know, it really depends on the science that you want to do. You guys have any questions? You've been hearing me talk for a while. Or like, what's your guys' background, or what are you? What's the class about? What's that?
Somebody else go first. We're gonna cover,
Okay, cool. And what are you guys observing with, and what data are you using?
Well, we haven't done any observations ourselves so far for this lab, but a lot of it's data that we've been working with, and stuff that's already started.
Okay, so it's like from the archives,
Yeah.
from the telescopes. Okay, awesome. You say it was like Gemini stuff, or is it from?
We have been using GMOS data.
Oh, awesome. Okay, I grew up on GMOS. I started undergrad at Santa Cruz when GMOS was being built. So I was like next door to the office of the person who was building it, and then I was like, "Cool, can I use your instrument?" And they were like, "Well, you got to apply for time." Okay. But I first like GMOS came online, I think in 2003 or 2002, something like that. And my first observation ever on Maunakea was 2003 with GMOS. It's a cool instrument. I like it a lot, and it's been around forever, but it still works really well. They're even upgrading it now. They're about to make it more blue sensitive. New CCD, yeah. Evan Kirby, who actually is a Shuttle the Scientist friend, and he was actually at Santa Cruz as a grad student when I was an undergrad there. He is a professor at Notre Dame now, and he initiated Notre Dame's really awesome at making instruments. They have cool instrument labs and all that kind of stuff, and so they built some new CCDs for charge coupled devices detectors for yeah. So I'm stoked on that, because that's what I need for my science.
So you use GMOS.
As Ekta alluded to, we actually got a big GMOS South program this semester. So I'm checking the night log every night, waiting for a call from Chile to say, "Hey, we're observing your targets." So it's actually a very distant forming supercluster of galaxies that Ekta discovered. So if you guys know Redshift, in general. So if I said Redshift 4.1, you would know roughly what that. Okay. It's out there. Yeah. Pretty far, yeah. So it's like universe is like 1.3 billion years old, something like that at that point. Yeah, so it's about 10% of its current age. And yeah, so things were very just forming. But yeah, Ekta found a bunch of these really massive structures in the early universe. So we're targeting one of them with GMOS, or we're hoping to anyways. It's sitting in the queue right now. Yeah, that's exactly right. Yeah, you can get it at the Hilo bottle shop here. I think that's the only place you can get it. And it's just for the Gemini staff, probably. Yeah.
So I think there's a ALTAIR mirror that you mentioned, how large is that mirror?
That's a good question. I don't know. I'm not sure. Do you know? It's not that big, honestly.
Okay.
Yeah, yeah, probably what Matthew said. So maybe half,
Okay, that's good.
third of a meter, half a meter, something like that. Yeah,
Because I was just thinking, like, if that was big, that'd be a real pain to maintain, I imagine.
totally. Yeah, yeah. So yeah, I mean, it's like it's clever because, yeah, you don't want to be putting a bunch of actuators on your big like monolithic mirror, right? Like that's a lot of weight to the ground. There's a lot of like cracking point. We have actuators in the mirror. We have active optics on the mirror and everything. But you know, like those fine movements, right? That you really, I mean, the wavefront is all distorted, and so you really want to do fine adjustments of the mirror. Much easier to do that on a small mirror, right? I mean, the primary mirror of Gemini, I don't know how many times, but it's a lot. And so kind of like segmented mirror, like Keck has or James Webb has, or the new like extremely large telescopes are going to have. That's a little bit easier. So Keck has, I think, 3 actuators on each one of their mirrors, the 36 mirror segments. And I'm not sure if they actually do full adaptive optics on the mirror segments, or if they have another like deformable mirror. But I think they probably could, honestly. So yeah, but we're a monolithic mirror, so it's just one big piece of glass. Subaru is a monolithic mirror, so one big piece of glass. Pluses and minuses, mostly minuses, honestly. So we, as Matthew mentioned, we're doing planned shutdown. This is our last night of observing for a month, or plan for a month. And one of the reasons why we shut down is because we have a monolithic mirror. So we have to do some mirror maintenance. And at Keck, they have this, they can trade out the segments all the time. So they, in between the 2 telescopes, they have like what looks like a Westworld lab, and they have like all their mirror segments like sitting there. And they can just like re-illuminize all their mirror segments, put them back on, pop them on and off, whatever. So that they don't actually have to shut down. We actually use protected silver rather than aluminum because we're IR optimized, but not this time. Yeah, so this time we're just going to do like a little bit of cleaning maintenance, but it's a lot of instrument maintenance and A&Gs. Yeah, so our acquisition and guidance system, it's just time. We're creaky. We have like pain in our joints a little bit, and so we need to do some stretching before we're ready to keep going. And that's true of our instruments and our telescope. So I know that there's going to be some work done on some of our instruments as well. And so Keck does that every once in a while, but we do it every year for sure. And the other issue is that if you, heaven forbid, you break a part of a mirror, which I'm not saying that saying any names, but there was 2 very big pieces of glass up on Maunakea that have been injured over the last couple of years, and that wait until things are repaired, and that can shut you down for a year, and it has. So yeah, I'm a big fan of mirror segments. It was technology that people thought couldn't be done. Like they think that the concept would work, and Keck was the one who revolutionized it. So James Webb is thanks to Keck for the belief in that kind of thing. And these big, like 30-meter telescope and all these, no way you could build a mirror that big monolithically.
Space big.
Exactly. Yeah. Yeah, we have to innovate here. And even like Keck's adaptive optics system was trained in LIC, so the smaller telescope. So there's all this, it's like fractal, right? Like you all build on each other, and science is a synergistic community where you have really awesome hardworking people at one site, and then people say that's a great idea, and then they port it over and they're like, oh, it doesn't work this way, but we can change it around some way, and so on and so forth. But we also
Make sure you're making sure we're getting over to like the higher investment.
Exactly, yeah, because like on LIC, like we could apply as grad students for telescope time, and we usually get it. And so it's like the operating cost of LIC, which is 1 ton, so it's like a 3-meter telescope. Well, it's orders of magnitude less than Keck. So what I was told when I first was observing on Keck is that it's $1 per second. it's now like $2 per second. So, and that's like for Gemini, it's taxpayer funded. So I don't want to waste any seconds that we can, where we should be on the sky speaking with. So we're going to another MAROON-X observation. Ah, right. Okay, go back. Yeah. Good. And yeah, Matthew, we're ready. So,
Okay.
we're good.
I'd like to ask a quick question there to all the students. How important is it for you to be able, as undergrad students, to be in the control room and to connect with the astronomers and the observing science team directly as you are progressing in your career, not only as students, but as you think about
I think for me personally, I observe with the UH-88 telescope. And so seeing a bigger telescope operate like this is really interesting for me because obviously this is like the next step up of what I want to do. I don't know about for you guys though. But
It's the same, like, I've used UH-88 before as well, and then you come in here and there's more than one monitor for tracking things like.
I'm not-
Yeah, there's it's very important just to understand like how operations go for a telescope, as well as just making any kind of contact with people that the telescope operators or people running the facility as much always help.
That's right, 13.
Not really. Second bad.
So these were some of the sounds you were referring to earlier to help reminders for when things, when exposures end and things like that. I love it.
Okay, so so we're slewing now. This is the observation that we're going to take next. And this is our observing tool. And this is what helps us set up during the day of the observation, so we can kind of pretend like we're observing. We understand like all the various optical elements of the instrument and all of our wavefront sensors, and basically we set up a sequence of observations in conjunction with the team that is proposing for the observations. This visualization here helps us to get situated for the observation that we're about to take, also during the day when we're getting things ready. So what you can see here is a digital sky survey image of the field that we're going to go to. And this is taken probably in the R band, so the visual red roughly. And this here is our peripheral wavefront sensor 2. So this is one that we use exclusively. So MAROON-X, which is the instrument we're about to use again, it only uses the peripheral wavefront sensor 2 or 1. And GNIRS, our Near InfraRed Spectrograph imager IFU spectacular instrument that uses the peripheral wavefront sensor 2. So we have this is our guiding star right here. So we have our peripheral wavefront sensor detector here. This is measuring the location of the star. It knows the difference in angular position between our target, which is here. It's very faint. You can't even see it in this image, and the guide star. And so it's keeping the telescope, it's keeping that relative position the same. So it means that if we're tracking the guide star well, we're also tracking the science target well. And there's this gravitational flexure which occurs. So basically, gravity is different for the peripheral wavefront sensor than the instrument. And so it causes slight optical distortions. And so an instrument that doesn't have an on-instrument tip tilt mirror like MAROON-X has, we actually have to reacquire due to this gravitational flexure every 45 minutes to an hour. But because MAROON-X has this internal tip tilt mechanism, it does the work for us. And so we don't have to do that. And so this is the basic picture of what we're looking at, like the schematic of what we're looking at. And Matti has just informed Nchung that we are guiding it at 200 hertz. So it's making corrections 200 times per second. And now, so if I go to the next screen. So now Nchung is getting set up on the science target, and it's very faint, but we're still getting 2,000 pounds. So that's enough to guide. Yeah. And then I think it's what, 1,800 seconds for the exposure. Yep. So we're going to start guiding now with MAROON-X. And it's going to pull again the star into the fiber. And this is a very faint star, so we're taking one exposure per 13 seconds. And so it takes a little bit of time to get there. This next one will do it. Yeah, I think you're ready to go. Yeah. Yeah, so we're getting most of the starlight into the fiber. So we're going to start the exposure, and we have 30 minutes.
Brian, what does the red and white line represent in
Which
the
one?
exposure count? So we see red line and we also see a white line in the exposure.
Yeah, it's photon counter is the one on the white. That's the one that I pay attention to. I've already that I'm not sure about.
Mhm.
See. Yeah, I'm not sure, Ekta. It may be some other aspect of the guider. I don't know enough about MAROON-X to know. I will say that we do have a measurement also not only of the number of counts that are coming in, but we are actually able to measure the scene as the observations are being taken, which is incredibly useful. And it's a pretty accurate measurement. So this is in the visual band, and you can see maybe the numbers are too small, but the values are 0.5, and there's a variety of different measurements. There's the X and the Y, and then the average of those two. Um, and it's reading 0.5 right now, which in the visual band it's incredibly good.
It's awesome.
Faint is this one? How faint is this?
This is a B-band magnitude of 19. But I mean,
Yes.
this is R of 80,000, right? Yeah, exactly. Because yeah, I mean, it's dispersing the light so finely that even 8-meter class telescope, normally 19 mag would be nothing, but so we observe its faint as like 25th magnitude, maybe. So that's more than a factor of 100 bigger than this stuff. What was your guys' observing experience on like 88, the 2.2 meter? Or was it solar system stuff or?
I'm currently doing classification of transits, sometimes like supernovae stuff like that.
Okay, yeah. The 88-inch is like a factory for like supernovae and like I had a student at IFA in Manila that was doing like long period asteroids, this kind of stuff, and she was on 88-inch like all the time, like 5 times a month.
Dolan doesn't.
It was Dave Dolan's student. Yeah, actually, she was studying high redshift protoclusters with me, and then doing asteroids with Dolan. Yeah, yeah. So from the closest stuff to the furthest away stuff.
Spans the whole universe.
Yeah,
Every.
and she's actually now an operator at
Denise?
SOS. Yeah, Denise. Yeah, yeah. She just actually submitted a paper that's it's going to be awesome. It's like 500 protoclusters in the early universe. So I mean, this is like in her spare time. She does this stuff. It's insane.
Where is she?
She's here. Yeah, yeah. She was operating even like just a week ago or so.
Nice, yeah.
Yeah.
Did Trinity and things that you guys observed, have you guys observed 250 maybe?
I've never observed of this line.
So.
It's a 9-inch telescope. 9 inches. I mean, I used to run a lab at my old institution. It was like 8, 9 inches. I mean, you can see some stuff.
I've shot it here and I shot it at cat, but I haven't actually used it.
Okay. Which instrument for tech?
It was their multi-slit spectrograph.
They have LRES. They have MOSFire and GMOS. MOSFire, yeah. So MOSFire, that's a kick-ass instrument. I love that instrument. We have a capability kind of like it in the south. It's called Flamingos 2, but we actually have to put masks in the optical path. With MOSFire, it has this configurable slit units, which is the same thing that James Webb has for near spec. It's like these it's called MSA, multi-slit arrays. And yeah, you could just press the configure button and like all these things, and then makes yours. Yeah.
Changing it.
Yeah. So for MOSFire, it's like these bars that come in. I think there's like 50 something of them, 51 of them, and 51 pairs. And so they move like this, and they can make the slit like wherever. And so you have your like acquisition image where you have your like stars in those little boxes, and then you can actually reconfigure after the acquisition, so you don't waste any spectral real estate on these stupid stars. You want to go to like distant galaxies. So that's super cool. When you mill a mask, you have to have the boxes there, and then just keep it there the whole time. So face to space. We actually mill masks for the Flamingos 2 instrument here. So like one of Matthew's job is to take our laser cutter and actually it's carbon fiber, right? For F2.
Yes, no, F2 is aluminum.
Aluminum, right?
And for GMOS is carbon fiber. I think we have some masks here.
So we only have one machine.
I didn't know.
Yeah. We used to have one in the south, but it was shared by several church sites, so it doesn't work anymore. Yeah, so my GMOS South program, I actually with Ekta was here visiting. Oh, she has one. Yeah. Yeah, so we have one of our masks. It was a little bit of a distortion when we cut that mask. Yeah. And yeah. That's exactly what Ekta is holding up.
states. So, them are not fine.
Yeah.
Two masses.
That's a lot of toothbrushing and putting the
Yes,
pin in, yeah.
a lot of work to get them done.
Yeah, do you want to show off what you have?
I have
Yeah,
one too. I have some.
I can give a little bit of background. Actually, I can share my screen real quick. So really quick background. So Brian already mentioned that we are going to observe a protostructure, but what are protostructures? So basically you might have seen pictures like this that are clusters of galaxies. So basically these are very massive systems that have lots and lots of galaxies in them. And when these clusters are forming in the early universe, that's what we call protostructures. So our team, we have discovered, I think I'm not sharing the entire screen, just 1 second. Share screen. Okay, let's see if we can find. Okay, so I've discovered 6 different protostructures in the early universe, and I've named them after the names of 6 senses in various Indian languages. So Drishti, Surabhi, Shravan, Smriti, Sparsh, and Ruchi. And here what we see is basically the density distribution of these structures. So you have very dense regions shown in red and then other regions shown in blue. So we know a lot about these systems. They are very, very massive systems. They have mass of more than 10 to the 14 solar mass, 14.8 solar mass. So if you put, for Indians, it's like crore solar masses. And for others, it's what? More than few million solar masses. So million, 100 million solar masses. So lots of solar mass, very massive systems. And so we know a lot about them, but for this very distant system, we still want to identify how many galaxies are in it, and we still want to map it better. And for that, we are planning to take more observations of the galaxies that can be potentially inside that system. And we are going to use Gemini South Telescope, as Brad mentioned. So here we have shown basically all the purple ones are kind of galaxies. And what you have to do is you have to basically identify like which of these galaxies that looks to be inside this structure space-wise, but then you have to identify if it is also inside that structure in the 3rd dimension, right, in the line of sight dimension. So here we have shown different mask positions that we are gonna observe using this telescope. So basically you have one mask here, and total 7 different masks. And these masks, so they kind of look like this. Okay, so basically what we have is things like this. So this is
You have all the things.
so this is an image of a Hyperion proto-superstructure. So it's not the one we are going to observe, but it's kind of similar to that. And as you can see, so what happens is in this image of sky, you see lots of little dots and they're galaxies. But not all of them are going to be inside this, because it's like, if you see my 5 fingers, they might look in the same direction. But if I do this, these 2 are in the different vertical, line of sight dimension. So it's kind of like that galaxies may look together, but in the 3rd dimension, they can be separated. And we want to identify even in this 3rd dimension, which galaxies are together. And if they are together, then they could be kind of part of this system. So here is the overdensity, this dense structure that you see here. And we want to target some of these galaxies, okay? So in this region, you can fit lots of different masks. So the size of this is not to scale, like this doesn't cover the entire structure, okay? This is like, if you want to scale it, you can fit like many of such masks on this image. I hope that makes sense. So, but just to give idea, basically, if you have this kind of galaxies, you want to select few potential galaxies, because you can only fit depending on the mask, you can fit like 80 galaxies or 100 galaxies or 50 galaxies, depending on which instrument you're using. So you want to identify like 50 galaxies in the given region that could be potentially inside the structure. So once you have identified that, let's say if you want to target this and some of the bright galaxies, then you put holes in this mask where your potential objects are going to be. And then the light from these galaxies are going to go through this mask to the instrument. So it will be kind of like light from galaxy to the mask, to the instrument, and then your instrument is gonna, use some sort of spectrograph to get you the spectrum of the galaxy that you can use to know more about exactly where your galaxy is, and then if they are in the system or not. So something like that. So yeah, I was very fortunate that I was at the Gemini North facility when our mask of the system was getting made. And we had the privilege of kind of participating in the mask making process. And it was kind of interesting because I didn't expect toothbrush to be part of this very advanced system. But basically what happens is you use very sharp laser to cut holes in it. And then sometimes if you see this little holes, so as it's cutting this little hole, in very few slits, the remaining thing wouldn't come off very quickly. So you have to push it a little, but you can't shove your finger in it and push it because you don't want to damage it. So you can use little toothbrush to put it out. So it's kind of interesting to be part of it. So this is, I think this is a fiber, right, Bren? What is it called again?
Carbon fiber, yeah.
Oh yeah, this is carbon fiber. We also have another.
Yeah, we have like the little fibers that little dangling fibers that come down. So even the chads that you push out, even after that process, like you can see with that, you have to take like a magnifying glass, and then you see like little fibers dangling, and so you have to use the toothbrush. So this all comes down to a toothbrush. All this like millions of dollars of technology, and you're taking a toothbrush to the carbon fiber mass. But any little fiber is going to occult light. It's going to stop light from coming in. You don't want that, or it's going to create defects in the data that come out. So you definitely don't want that. So we're armed with our toothbrushes at all times.
Yeah. So this is going to be the Gemini South masks that we're going to use to observe the structures that we have discovered. But before this discovery, we have used these kind of masks. Hold on, maybe those. So this is a GMOS mask, and hopefully you can see little slits in it. So this is a big GMOS mask. This is an instrument on the Keck telescope. And the idea is still similar. You put the slits on the galaxies you want to observe. So we had used many of these kind of masks to then, identify the galaxies that could be in this kind of systems. And then we have discovered the systems and mapped them well. So it's a very many years long process to kind of take all these observations and integrate them properly and then conduct the analysis. And I also want to say, so you might be able to see something very different. Hold on, let me show you. So do you see there are some rectangles and there are some squares, right? This is a square, this is a square. And similarly, even in this one, let's see if you guys can spot the squares. Maybe some squares, not this one. I think there is some square here. Oh yeah, it's a very tiny one here. This one. So basically, you have to observe the galaxies, right? And those are the slits. Another thing you also have to do is, Brian talked a lot about guiding, right? So you have to have some stars, at least for these instruments, that are that are in this mask. So basically, apart from using galaxies, you're also looking at the stars to make sure that your mask is aligned properly and it is guiding well. Because you can imagine that for whatever reason, if this is tilted a bit, so one of your stars will be observed. I hope you can see the little square here, a little square here, right? So if your one of star is here, and if this other square, if you don't see star in it, then you can deduce that for whatever reason my mask is not placed properly, right? So apart from this galaxies, you also have stars in it, and so that helps you align the mask properly, and it also kind of helps with the guiding process. And these are kind of specific instruments that require this kind of.
Sorry, I'll interrupt for a second on that point. So we don't actually guide with the stars in the masks, but we do check the guiding, right? And we check any optical distortions that occur during the observation. So like this is really important for MOSFire, right? We usually put a star on one of the slits so that we can track the movement up and down of the star over time. And that's because of flexure, that's because of differential atmospheric refraction and other optical distortions that can occur. And so that, I mean, the stars that we observe, that we put in the masks, those are like 15th to 18th magnitude, right? And then the targets are, let's say 23rd to 25th magnitude, right? So that's a difference in magnitudes, this silly unit that astronomers call magnitudes. It could be up to 10. And so every 2.5 magnitudes is a factor of 10 in brightness. So it could be that the stars are 10,000 times brighter than the objects themselves. And so in a single exposure, we're not going to see the galaxies, the very distant galaxies, but we will see a star. And so we can watch over time, does that star actually move a little bit? And then we know by inference, because we have a fixed optical element, which is this mask, that all of our galaxies are also moving a little tiny bit. And so we can make a correction when we're post-processing those data, and we can move just a little bit where we stack together all those images. It's like if you were, holding like the new iPhone camera. I just found out the new iPhone camera actually deals with jitter, because if you're like holding like this, you're just like taking a picture of the Milky Way and you go like this, but your hand's going to shake a little bit. But what it does, it's so clever that it just takes a bunch of images and stacks them in a central location so that it looks like your hand is not moving. And that's basically the same thing that we do with so we're at iPhone level technology here. It's toothbrush and iPhone level technology. In the end. Yeah, sorry. So I just wanted to say, like, that's why the stars are like 1,000 to 10,000 times brighter than the objects that us personally, our group is observing, and so that's why we do that.
Mm-hmm. Yeah, and I was going to say that, for this kind of instruments, you do need this kind of masks. But apart from that, you also mentioned MOSFire, and in that you don't need this kind of mask, but instead it has like bars that go on specific location, allowing you to make slits kind of on that spot. So it is much more. So instead of like having this kind of fixed mask, imagine you have like bars going in and just leaving enough space where you can have the slit, So in that, it has some restrictions because you can have slits in just some directions, but it also allows you that, for this marks, if we are observing and suddenly I think like, no, I want to observe here instead of where the slit is, we can't do much, right? Because the mask is already made. But if you're using MOSFire, you can just, you still need some work to do, but you can kind of, you can make that arrangement on while you are observing, and it allows you to modify your plan if needed. And it doesn't need like, few days to make this mask or something. So it's more flexible in that way. But you can only have few slits there compared to this. So it's a way of, and it's also infrared. So different instruments have different advantages and different limitations, is my point.
Yeah, but it's especially important to have that technology in an infrared instrument, because you do actually have to warm up an infrared instrument to place new masks in. So like for F2, Flamingos 2 in the south, we actually have to warm it all the way up, then take the masks out, put the new ones in, and then cool it all the way back down. And that process can be, weeks. GNIRS here takes weeks. So if you're, that's not a short turnaround. So if you need to do something quick, MOSFire, the configurable slit units take, well, if you don't have a crash, they take like, let's say 10, 15 minutes to reconfigure, maybe 5 to 10. But, if we want to reconfigure, we take the time that we have to mill the mask, to ship it to south to warm up the instrument, to place the new mass in the carousel, cool down the instrument, and then observe with it. So that's a much longer period of time.
Mhm.
But it's an interesting point that you raised because so in classical observing, what we call classical observing, where we're on the telescope, we're guest observers on the telescope. So when we go to Keck or we go to Subaru, we are in charge kind of our own scientific program, right? So like we can observe the things that we want to observe in that night within reason. So if we say, oh, no, never mind, we want to change things around tonight because its conditions are better or worse than we thought they were going to be, or we found something really cool that just happened. So then we want to observe that instead of what we originally planned for. That's possible. But for Gemini, we're a Q observatory, which means we take observations from all over the world. Proposals from all over the world, and then we observe those scientific targets for people. And so they have to set that up ahead of time, and they're ranked based on their scientific merit is ranked based off of what they propose to observe. And so they can't shift things around at nighttime. We wouldn't even necessarily know because we don't necessarily know their science. So we do the observations that we plan for, and if they want to change things around, they have to ask permission from our director or head of science operations and say, oh, we have something else. It's generally consistent with our scientific program, so can we switch from this target to this target? And so it's a different philosophy. And so for us, configurable slit units are not as important because those observations are set up well ahead of time. And if you want to change those observations, there's even an administrative process associated with that before you could even make any change.
Mhm. So Brian, in your case, then if somebody just kind of wants to join in for their observations, can they do that, or is that kind of not allowed? Or
Yes, yeah. Anybody can eavesdrop. So we allow eavesdropping. And in fact, I guess I was mentioning earlier that, yeah, I'm waiting for a call from Chile because I have eavesdropping on our program, ECTA, there. And so as soon as they slew to our first observation, they should be calling me and letting me know I'm slewing. And then I would, if I weren't asleep or, I don't know, playing with my 2-year-old or whatever, then I would VNC in and watch them do the observation. So I would get on Zoom, talk to the observers, and VNC in and be able to watch what they're doing. So I'm eagerly awaiting that call, probably over our shutdown. We'll at least get one call. And I will let you know, Ekta, if I get that call.
yes,
For
I
sure.
was gonna say, please let me know.
Yeah. I should probably we should probably get in contact over WhatsApp or something like that. So that way I can give you a heads up since you're in Gujarat, India, and it's not easy for me to just say, hey, Ekta, we're going. So yeah, but that will be exciting. And any PI can do that. So they can join and watch the observations if they like. And that's actually helpful for us because we get to know better. I mean, they know their science, we don't necessarily. And so we always prefer a collaborative effort here. And they can say, oh, no, actually, we don't care. Like, it's fine. Like, the clouds don't look so bad. You can keep going, things like that. We can't really make those decisions because we're bound by kind of scientific contract to not give data that are worse than what the PI requested. But a lot of times, so if like clouds, the PI says, I want like photometric skies, meaning no clouds. If a thin layer of clouds comes in, as observers, we would say, nope, no good. We have to pivot. We have to move to a different observation. But if the PI was on the call, like for example, if I was on the call and they were taking observations, and they were set up on my mask or our mask, and they were ready to go, you best believe that I don't care about that thin wisp of clouds. And I would say, go ahead, keep going.
Right. And it's also a dynamic situation, right? It also depends like at what point during the observing process you have clouds, and also if you have somebody right there, they can be like, we have already taken some observations. If there's some cloud coming in right now, it's okay. We can kind of consider that or put an image that, this image might not work, but then other images are fine. So don't move to some different target, like just keep taking
Right,
observations.
right.
or something.
Right.
So if you're gonna observe your target, when will you know?
Basically when they're slowing.
That's true.
Yeah, so there's not a whole lot of the time. It's a MOS observation, so there's a little bit of extra time with the acquisition and everything. Basically 20 minutes beforehand. Yeah.
There's a box that one thinks to do that, or?
Yeah, you can do you put like a note on your note on your program, and you say you let your contact scientist know you want to eavesdrop, and then we put it in the spreadsheet, and then we have a kind of well, people put it on our notes for the night, and they say nobody. Actually, we didn't even check that. Did we check the eavesdropping for tonight?
I think it was clean.
It was clean.
It
Okay,
doesn't know.
that's on the transition wiki, the thing that says like eavesdropping.
Many people do that often, and
Yeah.
also the times at least I've been on the observer side and I have eavesdropped. I called but nobody answered.
Yeah, we
Because could be any time during the night, right?
Exactly. Yeah. We
So-
called it PI that's based in Japan.
Yesterday.
Was it yesterday or 2 days
I
ago?
think
so.
2 days ago. Yeah. I don't know. All these nights are running together now. And yeah, it was 7 o'clock in the evening.
Yes,
The
in Japan
dinner time.
yes.
Yeah. And no, they didn't pick up.
No.
So yeah. So I mean, world-class observatory here, like taking the observations, like that was fun, but I guess they're reading or something.
Usually you call and send an email. Usually I get the email reply next day like, oh, sorry, I wasn't able to join, but thank you so much for taking the data.
Yeah. Yeah, the nice thing about Chile, like the difference time in Chile here is like I'm awake almost certainly for the entire time they're observing. So was it 7 hours right now?
Yep. Do you have?
Oh, right. Yeah. So so they'll finish their night pretty soon, and I think we actually got the night log because they had bad weather.
Yeah.
Yeah. But so it's basically like totally reasonable hours here. Yeah.
Right. So we can find time in March. Anybody wants to? Gemini time. We could do it, you stop.
Yeah, UH
Yeah, that
Hilo
would
has
be awesome.
a
we're-
it's like the UH, basically the UH.
Exactly, yeah.
Yeah.
And it'll be for spring of next year. That'll be cool. We're
Yes.
just very interested.
Do it,
So
guys.
just come,
Yeah,
we'll
if you
just
can
drive
think-
up.
if you can think of something.
No pressure, we'll bring the Pisco, whatever.
Yeah.
Be cool.
Actually, UH is normally undersubscribed for Gemini. It's the only partner that's usually undersubscribed. I have a colleague that I've been working with for 20 years who's at IFA Manoa. Roy Gal, probably, you know him.
Yep.
Yeah.
Yep.
So he was a postdoc when I was a grad student at Davis, and we've been working on these same, distant galaxies forever. And usually there's a supplemental call because people don't have like enough. There's not enough observations to fill like the time, and so he's always asking me like, we need Gemini time for anything, and we were using Keck and Subaru a lot, so we didn't. But now we definitely try for it. But I go to the US stack now. But this semester actually for 25A coming out, Gemini was pretty popular. Right, so it was like a oversubscription factor of 2 roughly.
GMOS or MAROON-X?
It was GMOS and MAROON-X mostly. GNIRS is getting a little bit more popular because we got the upgrades of the IFUs. So I spent actually the last 2 years. I'm GNIRS instrument scientist or co-instrument scientist, and we spent the last 2 years upgrading GNIRS with IFU integral field unit modules, and so we can now take IFU observations, both in high resolution and low resolution, with GNIRS. So it's becoming pretty popular. For the low resolution is 3x5 arc seconds. High resolution is like 1.2 by 1.8 arc seconds. So it's really for adaptive optics. Yeah.
You ALTAIR it or no?
Yeah. And actually we can use ALTAIR with the low resolution IFU. It's LGS plus P1 modes or super seeing mode. So this is okay, we're moving. I think this mode was commissioned in like 2015 or something like that, but it's It's a mode where we can make wavefront corrections on our peripheral wavefront sensor 1 rather than on the AO fold. And so we make non-local AO corrections, and so we get super seeing. So we
Offload it a little bit.
yeah, exactly. And so we get about a factor of 2 to 3 increase in the data rate impacts. So we get like 0.3 arc second resolution roughly with that, as opposed to like 0.15 with true AO. And the fact that we can do it at P1 means we can open up the entire sky basically to adaptive optics, whereas if we're using like NGS, right? It's like
Well.
yeah, exactly. It's 0.1% of the entire sky that we can use it for. So that's really helpful. Like I've used LGS plus P1 for my science. And in fact, for commissioning, we looked at an Einstein cross with an LGS plus P1. We had incredible conditions, but we compared natural seeing to this LGS plus P1, and it was just incredible, the increase in the resolution. We're getting pretty close to the end of the session, it looks like. So yeah, we're moving one more MAROON-X, right? It's about a 20-minute observation. Yeah, it's about 15 minutes, right? Yeah. So I think that's going to take us to the end. So this was MAROON-X all the time tonight. Another session, so Gemini any night, could be anything. And tonight it was MAROON-X heavy, but another night could be GNIRS, GMOS. We actually never know when we come in, so we have to be prepared for anything. And it seems like people were very interested in planets tonight. We actually, honestly, we barely left the galaxy my entire 4-night shift. So we've been mostly observing targets in our Milky Way. I'm hoping later tonight we at least get outside the galaxy. I'm not sure. Maybe a supernova will go off or something. One can hope. We do have this target of opportunity system where people anywhere in the world can trigger an observation on Gemini if they want. They have data from a smaller telescope, and they see that something is happening in the sky, something just blew up. They can request us to move to that location. So this is what's called a rapid target of opportunity. We'll get an alert here in the observing room. This happens fairly often. And then we have to basically immediately stop what we're doing and go to that observation. And so at all times we have to be prepared for something like that. It's really fun. Not for the person that was getting the observations previously though.
What's the turnaround time for that, Brian, for making the decision for that?
Oh, so actually the PI will put in a note in their in the program, and it'll either say this is a non-destructive RTOO. That's the language we use. So basically, you don't have to stop the observation that you're taking right now, but please go to it after you're done with that. Or a destructive RTOO. So that's basically like, we need this now. And so Gemini is built to be fast and agile. Our changing instrument time is less than our slew time. So we can be on that source, depending on how far away it is in the sky from where we're pointing, 3 minutes. And that's really where Gemini is better than a lot of other observatories, because we are just fast. Everything is built to be fast. We're agile. Subaru is slower. Keck is slower. Subaru is quite slow to move. And we are fast. We're fast switching instruments. We're fast to move.
Actually, we are guiding.
Case in point.
This has been a fantastic session. Have a great evening, and we'll see you next time. Aloha.
Thanks, everybody. Bye, Jamaica. Bye, Ekta.
Thank you, Ekta, for the explanations. Also nice. Thank you, guys.